Yes, indeed. I will tell you today about geometric constructions for sparse integer signal recovery. So actually, the first part of this talk, I have given at USC several years ago in the combinatorics seminar. Okay, but still, let me start with some notation. So first, let me define the notion of a Sensen matrix. So an n by d real matrix, where d is usually taken to be bigger than n, is said to be a Sensen matrix for L sparse signals, where L, referred to as sparsity level, is between 1 and n, if for every non-zero vector x in R to the d with no more than L non-zero coordinates, the image under this matrix A, so A times x, is not equal to 0. So this is equivalent to saying simply that no L columns of my matrix A are linearly dependent. So the motivation for studying the Sensen matrices comes from compressive sensing, which is a certain signal recovery paradigm. So now, so here's, so we specifically will be interested in such Sensen matrices with integer entries. And so the goal is to construct an integer matrix with bounded coefficients so that D, the number of columns, is as large as possible with respect to n, the number of rows. Okay, so now imagine that I have such a matrix. So if I do, then notice that for two vectors, x and y, with no more than L over 2 non-zero coordinates each, they are different from each other if and only if their images under multiplication by this linear operator A, if the images are different from each other. So this allows for essentially for image recovery or data set recovery, right, from fairly few measurements. Okay, so the advantage of using specifically integer matrices, well, there's several advantages, not the least of which is that in digital communications, we're hoping the constructions I'm going to tell you about might find applications. In digital communication, people often use integer matrices, right? It's very difficult to do communication with real numbers. So another motivation for specifically integer matrices is error correction. So notice that if A times x is not the zero vector, then its Euclidean norm is greater or equal than 1. Well, because everything, so if x is an integer vector, A is an integer matrix, well, the smallest positive integer is 1. So this means that that images of distinct vectors are distinct and separated from each other. So this allows for error correction, this kind of separation. Okay, so with this in mind, here's an optimization problem that I want to discuss. So we want to construct n by d integer Sensen matrices for L sparse signals such that first, the size of coefficients of A is small. Second, D, the number of columns, is large comparing to n, the number of rows, and L, the sparsity level, which is less or equal than n, and ideally as large as possible. So now the first results I'll show you actually allow the sparsity level to be as big as the number of rows, but for actual applications, the sparsity level is usually taken to be a lot smaller than n. Okay, so but in any case, with this in mind, here's our first existence results. So this is joint work with Diana Needell at UCLA and Benny Sudakov at ETH Zurich. So for all sufficiently large n, we prove that there exist n by d integer sensing matrices for n sparse signals. So you see the sparsity level is equal to this horizontal dimension, so that the size of coefficients is 1. So this means that these are 0 plus minus 1 matrices, often known as Bernoulli matrices, I guess. And D, so the number of columns, is about 1.3n. More generally, there exist such matrices. So if I allow the size of the coefficients to be up to k in absolute value, then D is big omega of square root of k times n. Okay. So let me perhaps say a few words about the proof of this theorem, which is probabilistic, and that perhaps is my only claim to a talk and probability seminar. Okay, so here's the idea. So first, we want to prove the existence of matrices with the sup norm equal to 1 and D about 1.3 times n. So right, so once again, the sparsity level being n means that every n by n submatrix of my matrix A is non-singular, right? So I want to construct sort of right. So think of it this way, right? I'm taking column vectors to be, say, vectors in Rn, and then I want as many of them as possible so that no n are linearly dependent. Okay. So our main tool is this very powerful result about random matrices of Bourgain, Wu, and Wood. So this is from 2010. So they prove that if M sub n is an n by n random matrix whose entries are 0 with probability 1/2 and then plus minus 1 with probability 1/4 each, then the probability that this square matrix is singular is no bigger than this quantity, right? 1/2 minus little o of 1 to the power n. Now, I should say that this result was a major development in the direction of an open problem, which asked for a construction of random matrices like this with 0, 1, and minus 1 appearing with equal probability, so 1/3 each. So that problem has been resolved since. So in 2020, I believe, Konstantin Tikhomirov published a paper where the conjecture that the probability that such a matrix, random matrix with equal probabilities, is singular is at most this. So this has been proved. But for our purposes, we actually don't necessarily care how we pick our random matrix. So this is, as for our purposes, this is as good as Tikhomirov's more powerful result. Okay, so then what we can do is form an n by d random matrix by using the Bourgain-Wu-Wood law, right? So I'm taking 0 with probability 1/2 and then plus minus 1 with probability 1/4 each. So then I have this matrix with subnorm 1, and any n columns of it form a matrix distributed. Oh, should I? No, okay, Steve. All right. So distributed according to this law m sub n, right? So then the question is, how large can I take D to be? Well, so notice that the probability that any n by n submatrix of A is singular is at most this quantity, right, from their theorem. So the total number of n by n submatrices in a n by D matrix is D choose n. So then by union bound, the probability that A contains an n by n singular submatrix is at most this quantity, right? So D choose n times the Bourgain-Wood probability estimate. So then it is possible to bound this binomial coefficient using the binary entropy function, and using this, we can actually obtain that this probability is strictly less than 1, right? So the probability of occurrence of a singular submatrix is strictly less than 1 for D less or equal than this bound than we obtained. So this means that the probability that there exist such matrices A with all non-singular n by n submatrices is positive. So hence such a submatrix exists. Okay. So for the second part of our theorem, so we want to prove existence of this n by D matrix with size of coefficients bounded by k, and now D being omega large of square root of k times n, so that again every n by n submatrix is non-singular. So another result from the same paper of Bourgain-Wood guarantees that now if I take an n by n random matrix whose entries are distributed with equal probability in the set from minus k to k, then the probability that such a matrix is singular is at most this quantity, right? So 1 over square root of 2k minus little o 1 to the power n. And then we play the same game. So again, we construct a random matrix using this law. So the probability that any n by n submatrix is singular is at most this quantity. Again, we look at the binomial coefficient D choose n, which is the number of all possible such n by n submatrices. And so again, by union bound, we have this estimate on the probability that there is a singular n by n submatrix. And again, we can push D as far. Our goal now is we push D as far as possible so that the probability of this singular submatrix remains strictly smaller than 1. So then the probability of a matrix with no singular submatrix remains positive, so such a matrix exists. And that's so that's the idea of our proof for this theorem. Now, of course, one can ask, well, how much bigger than n can D be in reality, right? So we get some bounds, but how true are these bounds? So another theorem that we prove in the same paper is that for any integers n greater or equal than 3, k greater or equal than 1, there exist n by D integer. Not there exist, and any n by D integer sensing matrix A for n sparse signals whose subnorm is k, D cannot be bigger than this bound. So you see, this is quadratic in K, but linear in N. So of course, in some sense, the most interesting case really is Bernoulli matrices, right? So where K is equal to 1. So in that case, we just have linearity in N. But still one can ask, well, can this dependence be improved? So, well, I guess in the ideal world, of course, we want D as big as possible, but this tells you that D certainly cannot be bigger than linear in N. Well, what about in K? So this bound K squared, is this the truth? That is like, well, that is definitely not the truth, because so there's a follow-up result of Kanyagin and Sudakov. So just shortly after, they were able to just modify our argument to show that for sufficiently large N, D has to be big O of K times square root of log K. And so you see the improvement from our result to theirs is K squared gets improved to K squared of log K, and then in fact, you see, so our original construction of this sensing matrices, so we don't really give a deterministic construction. Our argument is probabilistic. So Kanyagin and Sudakov are able to give a deterministic construction of such matrices with D greater or equal than this K to the power N over N minus 1 over 2 in case this quantity is bigger than N. Okay, so, well, now a natural question, of course, is, so is this dependence on K and N optimal? So the dependence on N is, it cannot be better than linear in N, but my suspicion is that the square root of log of K can probably be removed. So probably the optimal result here is big O of K times N. Here's an example, so very low dimensional example, but at least something to look at. So here's a 3x6 sensing matrix for 3 sparse signals. So K, right, the absolute value of coefficients is 1. So any 3 columns of this matrix are linearly independent. So so here's kind of a low dimensional example. Okay, so before I go further, any questions so far? Is everything okay? Yeah. All right. Okay. So this is the part that I actually talked about several years ago, and here's new stuff. So what if we now allow the sparsity level L to be smaller than N? Because you see in previous results that I described, L was tied to N. It was taken to be equal to N. Well, what if I take L to be smaller? So then there's a result from 2019, but it just got published this year, actually. This is with my former undergraduate student, Alex Shu, who's now pursuing his PhD at the University of Washington. So here's what we prove. So for all sufficiently large N, there exist N by D integer sensing matrices for L sparse signals, where L is now between 1 and N minus 1, such that the subnorm of my matrix is 2, and D is greater or equal than this quantity. So you see N plus 2 over 2 raised to the power 1 plus 2 over 3L minus 2. Now here's an observation in particular. Notice that if I take L to be very small comparing to n, so little o of log n, then d is bigger than linear in n, right? So because this lower bound gives me, so this lower bound divided by n tends to infinity, as n tends to infinity, if I take L to be little o of log n. Now, I have to say, so another advantage of our result is that it is deterministic. So we actually, in principle, one can obtain an actual deterministic construction from our argument, as I will indicate when I show you the argument. So for practical purposes and compressed sensing, they want sparsity level to be big O of log n. So there is definitely room for improvement here, but at least we were able to show that if you disconnect L and N, one can obtain stronger results than just linear, than D being just linear in N. Okay, so what I want to do next is I want to describe a certain geometric problem from which our construction comes. So it's a certain geometric covariant problem. Let me discuss this next. So suppose S in Rn is a set of k points. So the question I want to ask is how many hyperplanes, so how many parallel hyperplanes are needed to cover S? So the first observation, which is quite simple, is that you can certainly cover S by no more than k minus n plus 1 parallel hyperplanes. Well, provided k is bigger than n, but that's the interesting situation, right? So if k is less than n, then just take any so then the k points live in one hyperplane. So then that's that. But if k is bigger than n, then what I can do is I can take a hyperplane through n plus 1 points, right? Is it? Yeah. And then just use parallel translations. So the worst case scenario is that every parallel translation will cover no more than one of the remaining points. So this gives us this bound k minus n plus 1. So, okay, this number is sufficient, but then the question is it actually always necessary? So maybe one can do a lot better than this. So here's the question. Does there exist a set of k greater or equal than n points in Rn that cannot be covered by fewer than k minus n plus 1 parallel hyperplanes? So I'm looking for an extremal set with respect to this covariant property. Specifically, I'm most interested in a situation where my set lives on the integer lattice grid. Here's the particular setup I want to consider. So let t be an integer greater or equal than 1. And let me take this integer lattice cube, c sub n of t, to be the set of all points in the integer lattice zn with sup norm no bigger than t. So it's this integer cube centered at the origin in Rn. And let S be some subset of this integer cube. So one can ask how many parallel hyperplanes does it take to cover S? Well, so the first observation is that I can cover the whole integer cube Cn of t by 2t plus 1 parallel hyperplanes, right? So just take well, take, say, the one of the coordinates equal to minus t, so take that hyperplane and then take parallel translation of it. You will need 2t plus 1 total translated hyperplanes to cover the entire cube. So surely every subset of this cube is covered by 2t plus 1 hyperplanes. Now, furthermore, here's also a simple observation. So if S is a subset of this cube consisting of k points, then the following is true. So if no fewer than k minus n plus 1 parallel hyperplanes can cover S, then k cannot be greater than 2t plus n. And on the other hand, if 2t plus 1 parallel hyperplanes are required to cover S, so as many as to cover the whole cube, then k has to be greater or equal than 2t plus n. So it seems like 2t plus n is sort of the key number, right? So this leads to the following question. So does there exist a subset S of this integer cube of cardinality 2t plus n that cannot be covered by fewer than 2t plus 1 parallel hyperplanes? So in general, for an arbitrary t, I still do not know the answer to this question, but we were able to answer this question for t equal to 1, which already leads to some results. So if t is equal to 1, right, then I'm considering all integer points with 0, 1, minus 1 coordinates. So for each n greater or equal than 1, we prove that there exists subsets S sub n of this integer cube Cn of 1 of cardinality n plus 2, right? So in this case, 2t plus n is precisely, well, 2 plus n, so n plus 2, which cannot be covered by fewer than 2t plus 1, which is 3 in this case, parallel hyperplanes. So there are many different ways of constructing such sets. So let me show you some examples. So here's one example. You can take a set Sn to consist of the origin, then the standard basis vectors E1 through En, so that's n plus 1 vectors, and then the vector with coordinates minus 1, minus 1, minus, so all minus 1 coordinates. So this set is an example of a set satisfying proposition 6. So here's another example. So you can take the the first vector is just the vector with all 1 coordinates, and then additional vectors are this, right? So the sum of all ej's up, well, starting from n minus I plus 2 to n, and then minus the n minus I plus 1. So this again contains n plus 2 points. Now, more generally, what one can do is you can take any set consisting of the origin and vertices of any simplex which contains origin in its interior. Now, of course, in general, a set like this does not necessarily live on the integer grid, but any set like this will have this extremal property. Right? So if you take this simplex, so vertices of the simplex plus the origin in its interior, then this set of points cannot be, so it's a set of n plus 2 points, and it cannot be covered by fewer than 3 parallel hyperplanes. And so that's not difficult to prove also. So now let's go back to sensing matrices. So how does our covering problem relate to sensing matrices? So what I can do is take k to be greater than n, and let x1 through xk minus 1 be distinct non-zero vectors. Let S be the set consisting of these vectors and the origin. And now let A be n by k minus 1 matrix whose columns are these vectors. So if S has this extremal property that it cannot be covered by fewer than k minus n plus 1 parallel hyperplanes, then it turns out that A is a sensing matrix for n sparse signals. But you see here, K is not right. So for instance, if we take our set from the previous proposition 6, then that consists of just n plus 2 points. So my sensing matrix will be n by n plus 1. Well, that's not super impressive or interesting for that matter, right? So one can ask, well, can we do better? And it turns out that one can push this covering construction a bit further and do a lot better. So to do this, let me define this notion of difference sets as we use them. So let me take a set S of k points in Rn and partition it into 2 disjoint subsets. So I'm going to call the subsets I sub m and j sub l, where m and l add up to k. Right? So I just partitioned my set S somehow into 2 disjoint subsets of cardinalities m and l, respectively. So then let me define the corresponding set of pairwise difference vectors. Right? So I'm going to take all differences xi minus xj, where xi comes from the first set in my partition and xj from the second set. So then the cardinality of such difference set is no bigger than m times l, which is m times k minus m. Okay. So now for any subset D of the set of all difference vectors, let me define its support to be the set of all distinct vectors xi that make an appearance in this difference vector. So let me give you an example. Suppose, for instance, I take the difference set, so x1 minus x2, x3 minus x2, x1 minus x4, and x3 minus x4. So then the support of this difference set is x1, x2, x3, x4, because they make an appearance in this set of difference vectors. Okay. So, well, I can now actually define a bipartite graph on this difference set as follows. So I'm going to take vertices to correspond to the support vectors of D, the way I just defined. And now two vertices, xi and xj, will be connected by an edge if and only if the corresponding difference vector, x minus xj, belongs to my difference set. So this is a bipartite graph, right? Because so one partition is my set I sub m, the other partition is my set j sub l, right? So they're disjoint, okay? In other words, I'm thinking of the set of difference vectors as the set of edges of this graph, gamma of D. So let me also write G of D for the minimal length of a cycle in this graph. So this is usually called the girth of the graph. So also let me write A of D for the matrix whose column vectors are these difference vectors, right? So elements of my difference set. Okay, so with this in mind, here's our kind of main geometric theorem that we prove. So suppose that S is a collection of k greater than n points. Now m and l add up to k, and I partition S into this disjoint sets, right? I sub m and j sub l. Then I take D to be some set of difference vectors, right? So So D is not the whole set of difference vectors, it's just some subset. Now let script L be between 1 and n minus 1. Remember, the script L is this will become my sparsity level. So the following two statements are true. First, if S cannot be covered by fewer than k minus n plus 1 parallel hyperplanes, so my set has this extremal property, and for every subset D prime of L vectors, the girth of the corresponding graph is bigger than L, then the Sensen matrix A of D has, then A of D is a Sensen matrix for L sparse vectors. So that's one direction. In the opposite direction, if for every partition into M and L vectors, so for every such choice of M and L, the corresponding matrix on the full difference set is a Sensen matrix for n sparse vectors, then the set S must have this extremal property that it cannot be covered by fewer than k minus n plus 1 parallel hyperplanes. Okay, so this proving this theorem was some work, but now that we have it, let me tell you how we can obtain our result about L-sparse Sensen matrices using also some machinery from theory of bipartite graphs. So specifically, there are some results of Lebezhnik, Ustimenko, and Walder from 95, where they provide a deterministic construction of bipartite graphs, a family, whose girth is greater or equal than L plus 1 on k vertices, and the number of edges is greater or equal than this quantity. So you see k over 2, and the number of vertices over 2, raised to the power of 1 plus 2 over 3L minus 2. Now, their construction is deterministic, but it comes from Lie algebras. So it's not a simple construction, but it is deterministic though. Okay. So now let S sub n. So let us start with a set S sub n of n plus 2 vectors with 0 plus minus 1 coordinates from our proposition 6. So remember, so this is the set of vectors on 0, 1, minus 1 grid that cannot be covered by fewer than 3 parallel hyperplanes. Sorry, it's a typo. This is supposed to be fewer than 3. Everybody can be covered by 3. Okay, now let me start with the set S sub n, and let me now partition it so that the corresponding bipartite graph on this set S sub n satisfies this bound 1 by Lebezhnik, Ustimenko, and Walder. So now let me take the matrix corresponding to this bipartite graph as I just described in our previous theorem. So since the girth of this graph is greater than L, we obtain a Sensen matrix for L sparse vectors whose subnorm is equal to 2. And so the construction of this matrix is, well, it's as deterministic as the Lebezhnik-Ustimenko-Walder construction, right? Because what one can do is start with our extremal set, then partition it using the sort of recipe from their paper, then build the bipartite graph that satisfies their conditions. So that's a deterministic construction, and from that build a matrix. So that's a deterministic construction as well. So then our matrix is an n by d matrix where d is greater or equal than this quantity. Right? So you see this bound comes directly from their bound, where I'm taking k to be n plus 2, because that's the cardinality of our extremal set S sub n. Okay, and now we notice that if we take L to be sufficiently small, so little o of log n, then it's just a calculus exercise to show that in that case, d over n will tend to infinity as n tends to infinity. So we built an example of a sensing matrix for L sparse vectors where the dimension d is bigger than linear as a function of dimension n. Here's an example. Consider the set S3 that I showed you before. So let me perhaps just remind you what it looks like. So so take this set S3, and on this set, build a matrix using the 3-2 partition. So using this bipartite graph construction, so then we get this matrix A of D, which is a 3x6 sensing matrix for 3 sparse vectors. And so there you go. So that's an example of our construction. Okay, so I also wanted to tell you a little bit about a connected geometric problem, but let me pause here for a second and see if there are any questions before I proceed. So Steve, I have another, 5-7 minutes or so?
Yeah.
Okay, sounds good. So let me tell you then about a geometric problem which is closely connected to our covariant problem. So this is something called the Tarski plane problem. So this is, it originates, so Tarski was a logician, but he was also interested in some analysis in geometry. In particular, he formulated something that became known as Tarski's Planck problem. So let M be a non-empty convex compact set in Rn. Now define its width, W of M, to be the smallest distance between 2 parallel supporting hyperplanes, right? So I'm taking 2 parallel hyperplanes so that M is fully in between of them. And then I'm taking the smallest distance between such 2 parallel hyperplanes. That's called the width of my convex set M. So now a Planck in Rn is simply a strip of space between 2 parallel hyperplanes. And the width of Planck, so if P is a Planck, then H of P will denote its width. That's simply the distance between these 2 parallel hyperplanes. Now, so in 1932, Tarski formulated the following conjecture. So he said, suppose that you have some collection of Plancks, not necessarily parallel, but a collection of Plancks that covers the set M. Then, says Tarski, the sum of width of these Plancks has to be at least the width of this convex body. So if you just think about it for a minute, it seems intuitively clear, right? How can it be any other way, right? So this is a common feature of many problems in convex and discrete geometry, that they seem intuitively clear and then turn out to be surprisingly difficult to prove. So Tarski himself was able to prove this conjecture in the plane, so in 2 dimensions. And then almost 20 years later, Bang proved it in general, a very clever construction, so very ingenious proof. But in any case, so this is a theorem now. This statement is true. Well, so the simplest possible such covering, right, by planks is by parallel planks. But what if I impose an additional condition? So suppose that I mark some number of points inside of M, and I say, I now want you to cover my set M by parallel planks so that these marked points are not in the interior of the planks. So they can be on the boundary, right? So on support and hyperplanes of my planks, but they cannot be in the interior. So the question I want to ask is, with this condition in mind, how wide can